All right, so I'm going to look at the same problem that we had looked at in class and try to review sort of sinusoidal steady-state issues. So if I'm given a circuit like the one that's shown here, and I'm given a input voltage that's sinusoidal, and I want to figure out the current, I'm going to have to write a differential equation to do this. But the differential equation is obviously going to become a lot more complex. Okay, so let's do this, and let's remember we're going to do this in terms of the given parameter values. So we are given parameters here, Vm, omega, R, and L. Essentially, all of these are just numbers, right? These would just be numbers. But we're going to keep it symbolic, because when we keep it symbolic, we can gain a lot more intuition about what's going on in the given problem, okay? We'll look at that separately later. But I'm going to keep it in terms of those parameters. We're going to treat them as if they're numbers and solve symbolically. So I'm going to write my KVL going around the loop starting at the bottom corner. So 0 equals minus Vm cosine omega t plus Vr plus VL. I'm going to just define those guys here. Here's Vr. Here's VL, like that. Okay? Now, I can write here VR just in terms of my constituent relations, my Ohm's laws. I have VR equals IR given the polarities here, and VL equals L di by dt. Okay? All right, now I rearrange everything, bring the source on the left side, and then bring in the I values over here. So IR plus L di by dt. Okay? All right. So, where do we go with this? Okay? Well, what we do is we ultimately want to figure out what is I of t equal to. Okay? Now we know that that I of t always has a steady state component and a transient component. In terms of differential equations, we would call this the particular solution, and this we would call the homogeneous. All right. Now, the way that we did this, all right, is we think of the steady state is the solution that results from sources, right? Results from sources. And does not go away. This guy does go away and represents the effect of internal energy storage in the circuit. Okay. This part, essentially, we know, right, should have the form A e to the st, right? We plug that into the homogeneous differential equation and we figure out what s is, okay? We're going to skip that. We know this guy eventually goes to 0 as t goes to infinity. All right? We are much more interested now in sinusoidal steady state. In other words, what happens after the transient goes away. So in this particular case, what we know, what we guess, we want to solve these things, we guess a steady state solution of this form, omega t plus phi. All right, this form is important because what it says is that I'm guessing that the solution has the same frequency as the input, but a different amplitude and a different phase angle. All right, so in other words, something like this. Here's t. All right, here is, all right, not a great drawing, but not too bad. All right, here's a cosine waveform, like this. So this would be Vm cosine omega t. Well, I might have this might be my I of t, my I steady state, where this gap here, this is what I call phi. All right. In other words, I'm assuming that they have the same frequency, but they're shifted from each other and maybe have a different amplitude. All right. Now, it is typically easier if I say, well, that I steady state, which is I cosine omega t plus phi, I can use the trig identity to write it separately, right? So the trig identity, it's given in, it's either section 8.1 or 8.2 of your book, is that cosine A plus B is the same as cosine A cosine B minus sine A sine B, like that. I can use those same relationships. Okay, so here I use that relationship and say that this is I cosine phi cosine omega t minus I sine phi sine omega t. So what I see from that is I have two amplitudes here. I call this guy I1 and this guy I2. I say they're amplitudes. Phi and omega, phi is a constant, right? So is I a constant. It's only this cosine omega t piece and sine omega t piece that vary with time. So I can think of these I cosine phi and I sine phi as amplitudes. I can think of them as constants because the phase shift does not change once I'm in steady state. We saw that in the circuit in class, all right? We'll look at that again later. All right, so I can see from this that I1 is equal to I cosine phi, and I2 equals minus I sine phi. Okay, we'll come back to that later, but I can write this as I1 cosine omega t plus I2 sine omega t. Now, what do I do with that? Well, I plug this back into our original equation. So our original equation was Vm cosine omega t equal to I r plus L di by dt. So we plug this guy into that equation. So that says that I have r times I1 cosine omega t plus I2 sine omega t, like that. And then I have L times the derivative of that current. All right, so L times d by dt of I1 cosine omega t plus I2 sine omega t, like that. Okay, so the first part of this is easy. The resistances, those guys, this term, the first term here I don't change much, but the derivative I have to worry about a little bit. So this, all right, let's just kind of focus on that guy for a second. If I take the derivative of cosine, the derivative of cosine is minus sine. So I write this as minus L times I1 times omega sine omega t. Right, when I take the derivative d by dt of cosine omega t, it is minus omega sine omega t. Remember, the omega comes out. So that puts in omega L I2 cosine omega t for the other term. Okay, derivative of sine is cosine, derivative of cosine is minus sine. So I take these terms that I've just created here and I combine them with the other two we had for the resistive piece. And I get that this whole thing, I'm going to rewrite this guy a little bit differently. I'm going to group cosines and sines. So I'm going to group my cosine terms. I'm going to say I have R I1 plus omega L I2 times cosine omega t, and then I'm going to group my sine terms. I'm going to say plus RI2 minus omega L I1 times sine omega t. Okay, so all of that has to equal Vm cosine omega t. Remember, what we're trying to do is we're trying to get the two sides of the equation to match here. So looking at this, I see that I've got cosine terms and I've got sine terms. So what I can see then is I know that Vm cosine omega t has to equal Ri1 plus omega Li2 cosine omega t. Right, so the cosine terms go away, and I see that 0 has to equal Ri2 omega L1, right? Because there is no sine omega t term on the other side. So essentially what I've turned this into is two equations and two unknowns, right? Those two equations are Vm equal to Ri1 plus omega Li2, and 0 equals Ri2 minus omega Li1. Okay, so I see that I left that out up here. Okay. All right. So I've got two equations and two unknowns. The two unknowns here are I1 and I2. So I go about trying to solve this guy. So the first thing I do is I say that I1, I'm going to solve it for the simple equation. I1 must be Ri2 divided by omega L. Okay? I take that and plug it in over here. Okay? So I see that I get R. So when I'm plugging in for I1 over here in the other equation, I get R squared I2 over omega L plus omega Li2 all has to equal Vm. So that tells me, so I have to get a common denominator in this equation, so I get omega L on the bottom. So this ends up with R squared plus omega L squared, all of that times I2. So I see that I2 has to be equal to omega L over R squared plus omega L squared times Vm. All right. So all I'm doing here is getting a common denominator here, and then I'm rearranging to solve for IL. So a couple of things that we're gonna make some sense of here in a couple of days is we see that eventually what we're gonna see is that omega times L has units of ohms. Okay, and so what this turns out to be is ohms over ohms squared times Vm, which if you look at that carefully has units of amps. Okay, so we'll see, we'll get some meaning to that a little bit later in the next couple of lectures, but for now, okay, we see that we've got some relationship that's developed. I take this and I plug it back into I1, to this equation. That tells me I1 is equal to R over R squared plus omega L quantity squared times Vm. Okay, so we have our two results now. Okay, got the two results, and I know the two amplitudes back here in this equation. Okay, but I want to get back ultimately to this equation, which means I need these two amplitudes. Okay, so I know that I1 is equal to I cosine phi, and is also equal to R over R squared plus omega L squared Vm. I also know that I2 equals minus I. Ooh. Oops. All right. All right. Sorry about that. All right. I2 equals minus I sine phi, and is also equal to omega L over R squared plus omega L quantity squared times Vm. Okay? So how do I use that? Well, one thing I can do is I can say, well, if I took I1 squared plus I2 squared, I see that would be I cosine phi squared plus minus I sine phi squared. That would work out to be I squared times cosine squared phi plus sine squared phi. Well, cosine squared plus sine squared is equal to 1. Okay? So I see that I squared is equal to I1 squared plus I2 squared. Okay. All right. So I can easily start to combine these things now, and I can see. All right. Well, so put in I1 squared. Well, that's R squared Vm squared over R squared plus omega L quantity squared squared plus omega L squared. So this is, I'm putting in the I2 term now. Omega L squared times Vm squared over R plus omega L squared squared, like that. Okay? I can easily see that I've got the same term on both sides. So I've got a common denominator. Okay? Common denominator. And on top here, if I combine, I get that. So one of the things I notice is I've got a cancellation off the bat, right? I've got the same term on the bottom as I do on the top, all right? And since I squared was equal to this, I can take, so it was I squared, not I2 squared, I squared was equal to that. All right, I can say that I is equal to the square root of that whole thing. You take the square root of what's over there, and you would end up with a square root on bottom, like so. Okay? All right, so what do? I take that result now. All right, I take that result now, and what do? Well, I've got now the I part of the two expressions. Now what I gotta do is I gotta figure out the phi part. I've got the amplitude of the current. Now I need the phase shift. So to figure that out, the way I look at this is I say, well, if I take I2 over I1, that's equal to minus I sine phi over I cosine phi. Obviously the i's cancel. I get that this is minus I sine phi over cosine phi, but sine phi over cosine phi is tangent of phi. Okay? Now that has to equal to, since this is I2 over I1, I put in the two expressions for I2 and I1. So in other words, I put in omega L over R squared plus quantity omega L squared times Vm. And over here I put in R over R squared plus omega L quantity squared times Vm. So what happens? Well, the Vm terms cancel, the denominators cancel, and this guy becomes simply omega L over R. So what I find is that tangent of phi equals minus omega L over R, or that phi equals the minus arctan of omega L over R. So okay, I take this result here, I take this result here, I combine those two back into my original expression here, right? And I see that my current, my steady state current, is simply I cosine omega t plus phi, or in these terms, I write it like so. Okay. Now, we have to put a little bit of physical meaning to this, right? Because we see, kind of a couple of important points, right? One of the things I want to point out is, well, let's say if I look at this thing, what I can see is intuitively the amplitude. Remember the input. Let's just remember this: the voltage applied to the circuit was Vm cosine omega t. All right, let's compare these guys. If you look at this very, very carefully, right, we see, a couple of different things. We see that the amplitude of the current is a little bit different than the amplitude of the voltage, right? I also see that there is a phase shift, okay? And that phase shift depends on that arctangent function, okay? So that's kind of an important effect, right? So I want to look at this kind of intuitively and say, well, what happens if omega is really small? So let's say omega is approaching 0. If omega is approaching 0, then I can say that I steady state is approximately Vm over, well, if omega is approaching 0, I can say the omega L term is pretty minor, and I get Vm over square root of R squared, right? Which is simply just going to be R times cosine of omega t. Now I'm gonna say it's approaching 0, so it's getting small, but this thing is still a cosine. It's still varying, right? Maybe what I should really say is I want omega L to be much, much smaller than R. All right, so I write that as much, much smaller than R. So if it's much, much smaller than R, but so not necessarily 0, but much, much smaller than R, I get this result. And if I look at the arctan function, if this is also true, it's like I have the arctangent of essentially 0. So which angle has a tangent of 0? Well, that works out to be 0. So this guy is Vm over R cosine omega t. Okay? So what we're saying is if the omega L piece is much, much less than R, which could be because the frequency is close to 0, right? Essentially what we say is the omega L term in the denominator goes away, and it's as if the circuit was just a resistor. Okay? It's as if the inductor didn't really mean anything. Now, the other alternative would be omega L much, much greater than R. All right, which says that the inductor is really important, or maybe that omega is getting to be infinity. Okay, so the way I write this is I can say that steady state is equal to Vm over, now I can ignore the R part, so I have omega L quantity squared, like that, times cosine omega t. Now in this case, this gets a little bit tricky here. If omega L is much, much greater than R, then my arctangent is actually heading towards infinity, right? So omega L over R, if omega L is much, much bigger than R, that means that omega L over R is potentially getting very large, right? If I look at the arctangent function, okay, right, if I look at the, so here's theta, here's arctan theta, what you would see is it looks something like this, right? Basically varies between minus 90 degrees and plus 90 degrees, like that, right? So what I find is that if the argument omega L over R gets to be really large, this guy's going to approach 90 degrees, and so this guy's going to become approximately Vm over omega L times cosine omega t minus 90 degrees, okay? So sort of the important meaning of this is that, well, when omega L is tiny, right, meaning that the frequency is low or the inductor is small, it looks like my circuit's just a resistor, right? And the current that I get is just like what I would get if I had a resistor. In other words, this looks like the same current I would get if I had this Vm cosine omega t and an R like this, right? This looks like the result that I would get if I have just an inductor, okay? The important thing about this guy is it looks like the effect of the inductor is not just to change the amplitude, but to cause a phase shift, all right? In other words, it looks like the current here is lagging the voltage, all right? That's something we got to think about a little bit, all right, later on. Now, I included in this, all right, I've got a little bit of a Matlab plot here, all right? So I've got a Matlab plot. So what did I do? I basically said, all right, I have my input V cosine omega t. In this case, I chose 2 pi 60, all right, from my omega. I have R equal to 1 ohm, and I have L equal to 1 millihenry. In fact, I'm going to make that even a little bit smaller. I'm going to make that guy a microhenry. All right. In other words, I'm trying to make L really tiny. And notice here, okay, I've got my I equation. So this is my amplitude. And then in Matlab, I write A tan. Okay. A tan is how I get the arctangent function. Okay. So I run this guy. All right, and I get my result. There's actually 2 things plotted here. If I zoom in, okay, I actually see there's a blue and a red waveform in here. And if you think about it, if the voltage had an amplitude of 100 and R was equal to 1, right? If L is really small, I would expect very little phase shift, and I would expect the amplitude to be 100 divided by R, okay? So 100 divided by 1 would be 100, right? So input voltage divided by R, no phase shift. Okay, now let me choose a different L, all right? Let's make omega L now start to get a little bit bigger, right? So let's put this guy at a millihenry. All right, at a millihenry, now I can see the current, which is the red waveform, has gotten smaller, right? It's gotten smaller, and that makes sense if we look at this guy here. If omega L got bigger, then I have Vm divided by a larger number, which is going to make the amplitude smaller. And I'm going to start to have some phase shift now, right? In other words, tangent of omega L over r is starting to move this way, right? And I'm starting to move towards getting an angle, okay? And I can see here that there's definitely a phase shift. Now let's keep making that L bigger still, right? So let's make that L 100 millihenries. Now let's see. Wow, so now when I've made that L really big, the current has gotten to be really small, and it looks like this guy is now almost 90 degrees out of phase. And the reason I say 90 degrees out of phase, this is going to be kind of hard to see now, but it looks like, let me zoom in right here a little bit. So when this guy, when the voltage is going through a zero crossing, in other words, when he's crossing through 0 volts, I can see that the amplitude of the current is passing through a maximum. So that says we've got about a 90-degree phase shift. All right? And that's exactly what we predicted. We said that as omega L gets to be much, much bigger than R, right, that the, so when omega L gets to be much, much bigger than R, the phase shift is going to approach negative 90. But if omega L is getting very big on the bottom, then I'm dividing by a big number now. And so I would expect the amplitude of the current to get smaller. So the important thing, to kind of take away from this is, okay, if I zoom this back out, oops. All right, if I zoom this back out, is now for a big omega L, it looks like I've got about a 90-degree phase shift and a very small current. However, if I take that L value and make it small again, so now omega L is much, much smaller than R, it looks like they're basically in phase, and the amplitude is much larger. Okay, so we'll deal with a lot of examples of those, and we'll ultimately find a simpler way to solve this thing. I know it's complicated, but we ultimately find a simpler way to do it.